Hello everyone, I am Sunil Das, and today I will be presenting on the topic homogeneous equations in data science. This is topic of the subject ordinary differential equations and vector calculus at Institute of Aeronautic Engineering, CSE department. We are going to look at the skeleton that holds those boxes together. So when we talk about the data science, we often focus on the algorithms, the black boxes that gives us predictions. Let's start it. Learning outcomes. By the end of the session, we will understand what makes a homogeneous equation homogeneous, the difference between trivial and non-trivial solutions, and most importantly, how the rank nullity theorem helps us reduce reduce data dimensionality and extract meaningful features. Let's dive in. So in this, we will discuss about homogeneous systems, rank and nullity, data science application. Apply homogeneous equation concepts to dimensional reduction, features extraction, solution space. Explore the structure of solution spaces and the concept of trivial versus non-trivial solutions, homogeneous systems. Understand what makes a system homogeneous and how it differs from non-homogeneous equation. Learn how rank and nullity determines the dimension of the solution spaces in data science. So basically, what are homogeneous equations? The formula Ax equal to 0 contrasts is with the Ax equal to B, where B not equal to 0. In metric terms, it's a system where all constant terms are 0, written as Ax equal to 0. Now, why does this matter? Unlike non-homogeneous systems, which might have no solution at all, a homogeneous system is never consistent. It always has at least one answer that tells a trivial solution where x equal to 0. In data terms, that's like saying if all input features are 0, the output is 0. It's logically sound but not very useful. A homogeneous system or linear system is one where all constant terms of 0 in matrix form where write is a x equal to 0 where a in ax equal to 0 a is an uncrossed matrix. X is the unknown vector and O is zero vector. Yes. The interesting questions that becomes, are there non-trivial solutions? Trivial versus non-trivial solutions. So what is a trivial solution? Trivial solution is x equal to 0, meaning all variable equals 0. Every homogeneous system has this solution. It's always valid, but often not interesting from a data science perspective. Non-trivial solutions, there's a solution where at least one component of x is non-zero. They exist when the system has more unknown than independent equations, rank less than n. In data science, non-trivial solutions represent meaningful patterns or relationships in our data. Think of it this way. If our data is a cloud of point, the null space represents the direction where nothing happens. If we move our data in this direction, the output of the system doesn't change. If the matrix A is invertible, we only get the travel solution. But if A is singular, meaning it has redundant rows or columns, we get infinite solutions of the space of our redundant features. If a variable is free to move without changing the result, it's a candidate for being removed. So instead of all rank, nullity, and big theorems. Rank A plus a nullity A equal to N. Now we reach the heart of the presentation, rank and nullity. Rank is the number of linearly independent rows or columns. It represents the true information content. Nullity is a dimension of the null space. Basically, the number of free variables or redundant dimensions. The rank nullity theorem states that the sum of these two must equal the total number of column n. In a high dimension data set with 100 features, if the rank is only 20, the nullity is 80. That means 80% of our data is noise or echoes of the first 20 features. Understanding the ratio is the first step in cleaning a data set before training a model. Rank R. Rank is represented by R, the number of linearly dependent rows or columns in matrix A. It tells us how many constraints we actually have. Second one is nullity, uh, n minus R, the dimension of the null space. It equals the number of free variables in the solution. Rank nullity theorem. For an n cross n matrix, rank A plus nullity A equal to n. It means rank plus nullity equal to n. The fundamental relationship governs solution structures, data science, and impact. High nullity means more degrees of freedom in solutions which relate feature redundancy and dimensionality reduction. Solving homogeneous system. First, we write in matrix form, express the system as Ax equal to 0. Then use use Gaussian elimination to get reduced row column from identify free variables, express general solution. Rather, solution as a linear combination of bases for the null space. A practical example. Now we are discussing about the applications. Let's bridge the gap between math and real world problem. How do we use this? PCA, principal component analysis. This is the most famous use. We solve the eigenvalue problem, A minus lambda I equal to 0. That's a homogeneous system. We use it to find the axis that captures the most variance effectively, ignoring the null space where data doesn't change much. Feature selection by identifying linear dependencies. Considering the system x1 plus 2x2 plus 3x3 equal to 0, uh, 2x and 2x1 plus 4x2 plus 6x3 equal to 0. When we notice the second equation, it's just twice the first. So we really have only one independent constraint. After row reduction, we get x1 plus 2x2 plus 3x3 equal to 0. Here x2 and x3 are free variables. We can express x1 equal to minus 2x2 minus 3x3. The general solution is x equal to x2 minus 2, 1, 0 transpose plus 3x3 minus 3, comma 0, comma 1 transpose. The null space is two-dimensional, so spanned by two basis vectors. Application in data science, principal component analysis. PCA finds direction of maximum variance by solving homogeneous eigenvalue problem. The null space reveals redundant dimensions. Feature extraction, then identifying linear dependencies among features helps remove redundancies and improve model efficiencies. Data compression. When this data is compressed, neural networks, the weight matrices in neural networks often have non-trivial full spaces, affecting linear dynamics and generalization, regularization, clustering. Homogeneous systems have identified natural grouping by finding common null space. Deep dive PCR homogeneous system. So basically, we use the eigenvalues problems a minus lambda equal to 0. Common misconceptions. Homogeneous systems are always trivial. False. While they always have their trivial solution, non-trivial solution exists when the rank is less than 0, less than n, which is common in real data. Rank nullity only matters for theory. False. It directly impacts feature selection, model complexity, and computational efficiency in practice. Null space is just zero. False. The null space is a subspace containing all solution to x equal to zero. It can be a it can be a high dimensional and a very informative. All features with linear dependence should be removed. Computational consideration, numerical stability, computational complexity, space matrices, practical tools. Case study, feature redundancy in customer bill. A retail company collected 50 customer features, including age, income, purchase frequency, and derived matrices. It analyzed. These are the formulas and definitions. Formula and definitions. Homogeneous system. X equal to 0, where A is an n cross n, X is n cross 1, 0 is n cross n. Definition, maximum number of linearly dependent rows or columns. Rank minus nullity. Rank A plus nullity equal to n. Nullity, dimension of the null space where number of free variables. Null space n of A equal to x belongs to R. Travel solution x equal to the eigenvalue problem A minus lambda I into V equal to 0. This is non-trivial solution, at least one common non-zero linear solution x equal to C1 V1 plus C2 V2 plus and so on up to CK VK, where n V1 to VK form a basis of n of k, versus minimal set of linear independent vectors spanning a space. So these are basically formulas and definitions of this, and these are very important. These are the key takeaways or notes. Homogeneous systems, A equals 0, always has a trivial solution, but non-trivial solution exists when rank is less than n. The rank nullity theorem, rank plus nullity equal to n, is fundamental to understand solution structure and data dimensionality. The null space reveals redundant features and linear dependencies that can be exploited for dimensionality reduction. PCA feature selection and regularization all rely on understanding homogeneous system and null spaces. In practice, use SVD for numerical stability and leverage libraries like NumPy and SkySpace. Learn for efficient computation. So in this, we discussed about homogeneous system and databases. Thank you. Homogeneous equations in databases. We discussed about homogeneous equations in databases. Thank you, everyone.